Hi everyone, and welcome to part 1 of Algebra 2, Lessons 6.5 and 6.6, Real Roots of Polynomials and the Fundamental Theorem of Algebra. So we're going to start out with some foundational concepts and I'm going to try and remind you of some things that you have learned in the past. So I have 4 questions right here that will help remind you of some content that you've probably learned in the past. First question is, what is the root or zero of a function? Then what must a polynomial equal in order for you to be able to factor it and find those zeros? When a number is a root, how do you write the factor of the polynomial? And finally, when doing synthetic division, what must the remainder be in order for the divisor to be a root? So pause the video, take a minute to think through those, and then hit play, and let's see what we have. Okay, a root or zero of a function is essentially the place where the function's graph touches the x-axis. We call it a zero because the y value is 0 because it's touching the x-axis. What must a polynomial equal in order for you to factor it? That would be 0 because we want the zeros of this. That's why we call them zeros. When a number is a root, how do you write the factors of the polynomial? Basically, if you know that the root or the zero of the function is like 5, you would write x minus 5. So you take an x, you write a minus sign, and then you write the root next to it. And finally, when doing synthetic division, what must the remainder be in order for the divisor to be a root? The remainder must be 0. That means that it divided evenly into that. So what we're going to do is we're going to take a look at an example where I'm going to give you the zeros of a function or the roots of a function, and we have to create a polynomial that will have those zeros. In this example, we're asked to write the simplest polynomial function with the zeros -3, 1/2, and 1. So these are the zeros. What we're going to do is write those binomials. It's going to be x minus each of these. Once your binomials are written, you just have to multiply them together. Now you pick any 2 of them and multiply them. I usually save ones that have fractions in them for last because that can complicate your multiplication and it makes it harder to finish the question. So I'm going to multiply x minus 3 times x minus 1. Okay, when I did that, I got x squared minus 4x plus 3 because x times x is x squared. To get this middle term, I combined x times -1 and -3 times x. I just added them together to get -4x. And then I did -3 times -1 to get +3. Now I'm going to distribute this x minus 1/2 into this polynomial here. Okay, when I distributed, I got x squared times x and -1/2, so I got this part. Then I did -4x times x and -1/2, and I got this part. And then I did 3 times x and -1/2, and I got this part. And I combined my like terms, and this is my final polynomial. So I just have to write p of x next to it, and my answer is done. Okay, so p of x just notes that it is a polynomial function. This is function notation. If they give you like give a y value, or they say y and x, you can put a y there. If they give you other names for your polynomial, you can put a different name there. But that's how this works. So let's take a look at more examples that are going to be very similar to this. But first, we have a few theorems to look at. The first theorem is the irrational root theorem. So if you're given roots of a polynomial that are irrational, and we know that the coefficients have to be like rational numbers that can be written as a fraction, then we know that this irrational root will have its conjugate root as one of the zeros. So if you notice that there is a square root 0, then there will be another one. It's just going to be the negative version of that or the positive version. So you just change the sign and you know that there are 2 of those zeros. The same thing is true for the complex conjugate root theorem. If you have an imaginary root, then you know its conjugate, its complex conjugate, is also going to be a root. The way I remember that one is that I have two i's and so does my polynomial. So if my polynomial has an I in one of its roots, it's going to have a second root with an I in it. And actually these two theorems are really helpful because they help us simplify our polynomial more easily. So let's take a look at some examples where I'm going to use both of these theorems. Okay, the first example is this one. It says, write the simplest polynomial function with zeros 3i and square root 2. Now, notice they've only given two roots here, but one of them is imaginary. So I can apply that complex conjugate roots theorem. The other one is irrational, so I can apply the irrational roots theorem. So even though they've only written two zeros, I actually know four zeros. You have 3i and negative 3i. You have the square root of 2 and negative square root of 2. So let me show you the work for this one. Again, I'm going to write out my binomials. I'm going to multiply them together and get my answer. Okay, when you do this, I always recommend multiplying the I factors together and then multiplying the square root 2's together. Because what's going to happen is all of the i's will cancel out, all the square roots will cancel out, and you're left with just regular numbers. If you mix it up and do this x plus 3i times x minus square root 2, you're going to get a very, very messy result. Notice what happened. These are a difference of two squares. You can follow the squaring pattern, or you can actually do the distribution and find out that the negative 3ix and the positive 3ix will cancel out. So the special pattern is that you square the first term, you write a minus sign, and then you square the next term. The reason that this says plus 9 is because when I squared 3i, I got 9i squared. The I squared is equal to negative 1, so it changed to this sign right here. I just multiplied those together. Now the same thing is true here. This is a difference of two squares because they're exactly the same, and the only thing that changed was this sign in between. So you square the x, you're at a minus sign, and you square the square root of 2, which just gets you 2. Now all we have to do is multiply these two together. So I did x squared times x squared is x to the 4th. X squared times negative 2 is negative 2x squared. And I combined it with 9x squared from 9 times x squared. And I got this 7x squared. And 9 times negative 2 is negative 18. The final step is to write it in polynomial function form. So all I needed to do was add the p of x onto it. Let's take a look at another example. This one's going to be a little more challenging because for one of these expressions, it's going to actually be like two numbers added together. Okay, in this example, it says write the simplest polynomial function with these zeros. Again, notice we have an imaginary zero here. This is a complex number. So we know that the other root of this is 1 minus I because that's the complex conjugate. And when I wrote my binomials, notice what happened. I wrote x minus 1 plus I and x minus 1 minus I. I don't need parentheses there because the minus sign will distribute, and because both the number and its complex conjugate are there, it's very simply a process of just changing this plus to a minus, and it's going to work out. So what I'm going to do first is multiply these two complex binomials together. And if I do it right, all of the i's should cancel out and I will end up with regular numbers. Okay, so I did x times x, I got x squared, x times negative 1, x times negative I. Then I multiplied the negative 1 in. Negative 1 times x, negative 1 times negative 1, negative 1 times negative I. Then I multiplied the I in. I times x, I times negative 1, and I times negative I. So I got this big polynomial right here. Now, if you combine like terms correctly, the negative xi will cancel out with the positive ix, and the positive I will cancel out with the negative I. And this I squared turns into plus 1 because you cross out the I squared, change the sign in front. The coefficient right here is a 1, so it's really a plus 1 right here. So this is what I got when I combined them. Now I just have to do the last multiplication of these two together. Now the order of multiplication doesn't matter. You can do x into this one, you can do x squared into that one and do the 3 terms multiplied. So I started with multiplying the x squared over to both of these terms. So I got x cubed minus 2x squared, then negative 2x times x and negative 2x times x times negative 2, and then 2 times x and 2 times negative 2. I combine my like terms, and this is my final polynomial answer. Okay, so that's how, if you have the roots, you can get the polynomial that would be the simplest polynomial that represents it. Make sure you join me for another video about how to factor polynomials.